Welcome. This screencast is going to start looking at the practice problems found on page 52 of the Brown SL Chemistry book. So question number 1 tells you have 0.100 moles of copper sulfate. It's hydrated with 5 water, and they want to know how many oxygen atoms could you expect to find in this sample. So first thing you need to do is you need to take your 1 mole of your copper sulfate, and I'm not going to write that out, but you need to figure out how many moles of oxygen would be in that. So for every 1 mole of copper sulfate hydrate, in this case pentahydrate, you should be able to see that there's 9 moles of oxygen. So we're really talking 0.900 moles of oxygen atoms. And then I could take that times Avogadro's number, which is 6.02 times 10 to the 23rd of anything in a mole. And that's where I came up with answer D, 5.4 times 10 to the 23rd. Question number 2, they give you this skeleton equation and ask what would be the sum of the coefficients when the equation is balanced using whole numbers. And this one, it can be a little bit messy to balance if you're using your rap sheet because it's not right away obvious that all you need to balance it is a 3 here and a 2 here, along with a 3 here. And when you do that, then make sure you count in that there's a 1 here. That 1 is assumed, even though we don't typically write it in. So this is going to give me coefficients of 9, or D would be my correct answer. And if you had some trouble balancing this, one thing to keep in mind is that you know the minimum number is 4, which isn't even a choice, but the only choices are 5, 6, 8, or 9. So if you had some trouble balancing this and you're getting bigger and bigger coefficients, you knew you were making it too difficult because 9 was the greatest number that was available. Question number 3 says 4 identical containers under the same conditions are filled with gases as shown below. Which container contents will have the highest mass? So really, you're looking for which one has the greatest molar mass because this goes back to Avogadro's idea that equal volumes under equal conditions will contain the same number of particles. So which one has the heaviest particles? Well, you need to know that nitrogen is N2, it's diatomic, so that means it's going to have a mass of 28. O2 is also diatomic and will be 32. Neon, you remember, is a noble gas, so it's going to be around 20. And then ethane, you may not have known, was C2H6. That's something I would give you on a test because we haven't done anything with organics yet. But given that equation, then you would see it was 30. So that means B, O2, is going to contain the greatest mass. So question number 4, I've written down the information they've given that 1 decimeter cubed of an ideal gas at 100 kilopascals and 25 degrees, which convert that to Kelvin, 298, is heated to 50 degrees or 323 Kelvin, constant pressure, so pressure is really a non-factor here. What's the new volume? So we can use the combined gas law and just ignore P, or you could think of it as being Charles' law. Either way, you've got V1 over T1 should be equal to V2 over T2, and that would be 1 decimeter cubed over the 273, or 298, I'm sorry, should be equal to my new volume over 323. And when I solve for V2, I'm getting a volume of 1.1, and that would also be decimeters cubed, which matches with C. Question number 5 wants to know how many sulfate ions you could expect in 100 cubic centimeters of 0.020 molar FeSO4. So the first thing is to find out is how many moles of SeSO4 is this? So if I have 100 centimeters cubed, I can divide by 1,000, and this is really 0.100 decimeters cubed. And 0.100 decimeters cubed times a concentration of 0.020 moles per decimeter cubed means we're dealing with 0.0020 moles of FeSO4. Then I need to know how many moles of SO4 would this be, and you see that there's 1 mole of SO4 ions per mole of FeSO4, so it's also 0.0020 moles of SO4. And expressed in scientific notation, this is 2 times 10 to the minus third moles, which matches with A. Number 6, they tell you 1.7 grams of NaNO3 with a relative molar mass of 85 is dissolved in 0.20 decimeters cubed or liters of water, and they want to know what the resulting molarity or concentration is. So what I need to do is take my 1.7 grams, divide by my molar mass of 85, and determine how many moles we're dealing with here. And so it's 0.02 moles of NaNO3. And then my concentration, my molarity, should be the 0.02 moles divided by the volume, which is also 0.02, or 0.2, excuse me, 0.2 decimeters cubed, which means my molarity is going to be 0.1, and you can put capital M, IB will recognize that, or moles per decimeter cubed, or moles per liter. At any rate, that matches with letter B. So number 7, they want to know, if you have this balanced equation and you're given 3 moles of aluminum, how many grams of hydrogen can you expect? Well, first thing is to look at the 3 moles of aluminum, look at the balanced equation and see that we can expect 3 moles of H2 for every 2 moles of aluminum, which means we can expect 4.5 moles of H2 to form. And then knowing that H2 is 2.02 grams per mole, this is right around 9 grams of hydrogen we can expect to form, which is letter D on your choices. Question number 8 tells you have a gas with a relative molecular mass of 56 and empirical formula of CH2. So if you find the mass of that empirical formula, it's going to be 14.03. The 56 is quite a bit more, so you go ahead and divide, and you see it's 4 times more. So you take 4 times the empirical formula and get C4H8, which matches with letter D. Number 9 wants to know again, what's the sum of the coefficients when the equation is balanced using the smallest possible whole numbers? And anytime you have a hydrocarbon being burned, it's easiest to balance the carbon first. So I put a 2 there. Then balance your hydrogen, which is balanced. And then look at my oxygen, and I've got 5 oxygen, which would take a 2.5 here. So I should be able to just double this to 2, 5, 4, and 2. And if I add that up, then I've got 13 as the sum of my integers, which matches with letter D. That's a 13 there, not a B.